Hey everyone. So today we are looking at section 4.4. This is going to be your last section from chapter 4 that we are going to talk about. So as you can see, we are talking about counting rules in here. So basically they are saying, many times a person must know all the number of possible outcomes. So what are your total possible outcomes going to be for a sequence of events? So this is where three of these rules will come into play, or your counting rules as we're calling them. So you will have the fundamental counting rule, which is the first thing we're looking at. And then we will also talk about the permutation rule, and we'll talk about the combination rule right over here. Okay, so let's start with our fundamental counting rule. So they are saying if you have a sequence of n events, so n is the total number of events you're going to have. So they're saying in a sequence of n events, and in which the first one has k1 possibilities, the second event will have k2 possibilities, and the third event will have k3 possibilities. And of course you can keep going depending on how many events are there in your sequence. We're saying the total number of possibilities. So remember, this is just counting the total number of possibilities. We are not counting probabilities here. We are counting the total number of all possible outcomes that our sequence of events will have. So this is where you take how many possibilities are in event 1, multiply that with possibilities of event 2, event 3, and so you keep multiplying. So this is going to be the rule we are going to be looking at. And then of course in this case they are talking about when it is saying and, it means you're going to end up multiplying those possibilities. So let's go ahead and take a rule at how this fundamental counting rule works. So here we're talking about tossing a coin and rolling a die. So toss the coin, toss the coin first, and then we will roll a die. And they want to know what's the total number of outcomes that you will get for these sequence of events, right? So of course we know when you toss a coin, you're either going to get a head or a tails, right? And after that you're going to roll a die, and of course your dice will give you anything from 1 to 6. So those are going to be these 6 events that you are seeing here. So depending on, do you get heads or do you get tails, these would be the number of events you will have. So the total outcomes we have, so all 12 of these together become your outcomes. And if you will actually remember, we had done this similar example, or basically the same example in previous section, in section 4.3 also. I had shown you how this would work out to be. So the way your fundamental counting rule will work, where we are multiplying these total number of possibilities. So the idea is you have 2 possibilities or 2 outcomes that we get from tossing a coin, right? You either get a heads or a tail. So those are your 2 possibilities. When we are talking about rolling a die, that's going to be any one of those 6 numbers, right? So those are 6 possibilities or 6 outcomes. So this is where you multiply your 2 different possibility for the number of outcomes. So 2 times 6 will give you a total of 12 possibilities. And of course you can see when we do this using a tree diagram, we of course end up getting the same result. So that's kind of where this fundamental counting rule comes into play. All right, let's look at this example here, number 2. So this one is talking about a paint manufacturer wishes to manufacture several different paints. So the categories would be color, and that's 1, 2, 3, 4, 5, 6, 7 different colors. The type of paint, so that's latex, and oil. So that's 2 different types. Texture can be flat, semi-gloss, high gloss. So of course that would be 3 different textures. And then use for the paint could be outdoor or indoor. So that's 2 different uses for the paint. So they're asking us how many different kinds of paints can be made if you select one color, one type, one texture, and one hue. So this is where again your fundamental counting rule will come into play. And you will notice here in the solution, and I'm trying to keep this on one page, so we've got 7 colors right here. We've got 2 types of paint, 3 types of texture, and 2 different uses. So you are multiplying 7 times 2 times 3 times 2, which comes out to be a total of 84. So you can come up with 84 different types or kinds of paint using all of these options. So again, you take each possibility and you multiply all of them together and you get 84 as your final answer. Okay, now let's look at example 3 over here. This is talking about the distribution of blood types. So of course we know there are 4 blood types. You have A, B, AB, and O. And then you can also have blood which could be Rh positive and Rh negative. And then they are talking about, of course, you can also classify the donor as either a male or a female. So they basically want to know how many different ways can a donor have his or her blood labeled. So of course, we are talking about 4 different blood types, right? Your AB, then AB together and blood O. Then your Rh factor can be positive or negative, so that's 2 possibilities for the Rh factor, and then of course 2 possibilities when we talk about the gender of the donor. So you're going to multiply 4 blood types, 2 for the Rh factor and 2 for the gender. So 4 times 2 times 2 ends up giving you a total of 16 outcomes, right? And then they are actually showing you the breakdown by also using the tree diagram over here. So you can see we're starting out with breaking it down with the 4 different blood types. Then each blood type gets broken down into Rh positive or Rh negative. And then of course further you're breaking each one of them down into male and female. So that will end up giving you a total of your 16 outcomes. Okay, so again, kind of helps to visualize, so you can do these tree diagrams to help you out. All right, so then we are saying when determining the number of different possibilities of a sequence of events, you must know whether repetitions are permissible, because you know if you're going to be able to repeat your events, it's going to change how many possibilities you are going to have, right? So let's see what we mean by that. Let's take a look at this one here. So they are talking about the first year the state of Pennsylvania issued railroad memorial license plates. The plates had a picture of a steam engine followed by 4 digits. Okay, so they are saying, assuming that repetitions are allowed, how many memorial plates could be issued? So basically, if you think about this, we are saying you have this picture of the steam engine, and then you have 4 digits after that. So if we are talking about repetitions are allowed, you could potentially end up with a number on your license plate, which could be 4444, right? All 4 digits could be the same number. You can have 9999 or 0000. So that's what they mean by repetitions being allowed. So that means when you are trying to calculate these possibilities, we are talking about 4 digits. So that's going to be, and there should be a little multiplication symbol here. So that's going to be 4 spaces, right? And then for each space, you can basically have your numbers going from anywhere to 0 to 9, right? Because you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these would be all your digits. And of course, that's a total of 10 digits, right? So that's why we are multiplying 10 times 10 times 10 times 10, which will of course end up giving us total possibilities of 10,000. And just a little note, they are saying that these plates were in such a high demand that basically Pennsylvania had to start bringing letters in so they could increase the number of possibilities. Okay, so this gave you 10,000 different options if we allowed repetitions in our numbers, in our digits, right? Okay, now what happens, let's say if they said, okay, no, we do not want repetitions. So if you've already used the number 1, then for the remaining 3 places, you cannot have 1 repeating, right? So you could not have like 1, 5, 7, 1 as your license plate. So if you've used the number 1 already, it should not show up again in the remaining digits. So they are saying the first digit in the plate in example 4 can be selected 10 different ways, because that means you are using anything from 0 to 9 for that first digit. So that's going to give you 10 options, right? But now when we move to the second digit, you know, it's kind of like when we were talking about, do you have a replacement allowed or not? So like if you took a ace out of your deck of cards and you don't put the card back in, then how your probability would change. So think in those same terms, but we're not talking probabilities here. We're just talking how many outcomes you are left with. So let's say you've already selected the number for the first place. That means for the second place or the second digit, you're only going to have 9 options left. Then for the third place, you will only have 8 options left. And then for the fourth digit, you would only have 7 options left. So you can see how this number starts going down. Instead of being 10 times 10 times 10 like we did in this first part, you're only going to have 10 times 9 times 8 times 7. And you will notice our number of possibilities goes down. And in this example particularly, it goes down by almost half, right? You will only have 5,040 outcomes instead of having 10,000 outcomes. So you can see, like I was telling you before, if repetitions are allowed and if repetitions are not allowed, it will change, will end up looking like, okay? So just this little summary here is saying if repetitions are permitted, then the numbers stay the same going from left to right. If repetitions are not permitted, then the numbers would decrease by 1 for each place as you go from left to right. So this might be something to remember when you guys are going through homework and exam. Okay? So this brings us then to the idea of factorial. Factorial notation is basically where it uses this rule where repetitions are not permitted. So your numbers start going down by 1 unit for each place as you go from left to right. So when you're talking about 5 factorial, it means you are taking 5 times 4 times 3 times 2 times 1. So you can see how with each place, your digit starts going down, right? The number starts decreasing by 1. And then of course, if you multiply these, then your 5 factorial would basically come out to be 120. And in that same way, you can see 9 factorial will start at 9 and then it will keep going down 9, 8, 7, 6 till you get to that 1 at the end. But with 9 factorial, you actually end up getting 362,880 different possibilities. One thing you want to keep in mind is when we are talking about 0 factorial, so they're saying a special definition of 0 factorial is that 0 factorial will equal 1. So you definitely want to remember this rule. And when we actually start talking about our permutation and combination rules, you will see that this factorial plays a big part in those rules in there, okay? So basically the general idea is whatever is your number n, you start with that number n and then you start going down by 1 unit till you get to 1 at the end of that sequence, okay? All right, guys, so we've talked about the fundamental counting rule. We've introduced the factorial notation. Now let's talk about permutations. So they are saying a permutation is an arrangement of n number of objects But here's the key thing. It has to be in a specific order, okay? And this makes a big difference between, are you doing a permutation calculation or are you doing a combination calculation? So if things have to be in a specific order, then we have to use a permutation to do those calculations. If order is not important, that's when we bring in combinations, okay? So let's talk about permutations here first. So our first example here is talking about a person needs to make up a 4-digit combination to open the lock on the garage door, okay? So they're saying the person decides to use 4 different digits from the first 4 digits. So they're saying they're basically going to be using the numbers from 0 to 3, but then we want to know how many different combinations can be made from that. So basically they can use 0, 1, 2, and 3, but now the idea is how many different combinations can they come up with where you have 4-digit combination lock. So basically the idea is for the first digit he's going to use in their combination lock, you will have 4 options, right? Because he will use anything from 0, 1, 2, and 3. But since they don't want the numbers to repeat, for the second digit, they will only have 3 options. For the third digit, they will have 2 options. And then for the last digit, they will only have 1 option, right? Which means they are basically using 4 factorial as their calculation. And as you can see, this will come out to be 24. So this person will be able to use the numbers from 0, 1, 2, and 3, and there will be 24 different combinations. Now, if I was this person, I would use everything from 0 to 9, because that will, of course, give you more combinations, because as you can see here with 9 factorial, you are going to get a lot more options, but of course, you are not creating a 9-digit you're not creating a 9-digit combination for your garage door, right? So even if you were using, let's say, and I'm gonna go here, even let's say we were creating a 4-digit combination for our garage door lock, okay, but we were using the digits anywhere from 0, 1, 2, 3 all the way to 9, right? So anything from 0 to 9, and you are creating a 4-digit combination. So that means, and again, we don't want repetitions in our numbers. So let's say for the first one, we would have 10 different combinations, right? Because I would use anything from 0 to 9. And then whichever digit I used, I would not be repeating it. So this number would go down. And now I would have 9 options to choose from. Then I would have 8 of the very last digit. I would have 7 options to choose from, right? So you are multiplying 10 times 9 times 8 times 7, which will end up giving you 5,040 options. And of course, you looked at this calculation when we were doing those railroad license plate examples. So look at this. Instead of using just numbers from 0 to 3, if you use the numbers from, basically this would be from 0 to 9, instead of 24 possibilities, you now have 5,040 possibilities. And you know, the idea is, the more possibilities you have, the harder it's going to be for somebody to break that code. Think about those. With those 24 outcomes, how easy it's going to be for somebody to keep trying those different 24 outcomes and finally find one combination which would open that garage door, right? And so not having repetitions and using the digits from 0 to 9, you end up with 5,040 different possibilities. Or you can say different combinations in this case. Okay, alrighty, so that was example 5. So in example 5, all objects were used up, but what happens when not all objects are used up? So that means if you had more digits you were choosing from, then not all of them would ended up getting chosen, right? Which is kind of what this little example I was talking about is doing the same thing. But let's look at example 6. So this one is saying that a business owner wishes to rank the top 3 locations selected from 5 locations for a business. So how many different ways can she rank them? So this is where we're bringing in the idea of the fundamental counting rule. So for the first position, you would, or first location, you would actually have 5 choices to choose from, right? So after you have chosen that first location, you of course will not be including it again in your calculation, which means you will not have any repetitions. So for the second choice, she would only have 4 locations. And then of course for the third choice, she will only have, I guess they didn't write it down, but for the third choice, she will now only have 3 locations to choose from, right? So that means she would be multiplying 5 times 4 times 3, which of course comes out to be 60 different abilities. So there's 60 different ways she could choose the top 3 positions for her business, right? So what they are saying is, for examples 5 and 6, you can actually think of them as being calculations for permutation, because even in number 5, the order would be important here, right? So how you would choose the numbers from 0 to 3 would make a difference. And then also in the business location, of course, this would be the top first location, then the top second location, and top third location. So that order is going to be very specific, and the order is going to matter. So that's why we would say that both these examples are basically the idea of permutation. So just as your permutation rule 1, we have, if you take the arrangement of n objects in a specific order, and out of those n objects, you are only using r objects at a time. So you're not using all of the n objects, which would be like we had 5 locations, but we're only looking at the top 3. So that's 5 for the total and 3 as the r objects that we are choosing. So they are saying this is called a permutation of n objects taking r objects at a time. And this notation is important. So you're actually writing this as sub n, then p for permutation, and sub r, and this is actually how we define our permutation rule. So that's n factorial, that's the total number of options we have available, and then divided by n minus r. So that's out of the total of n, we are only choosing r, so that's n minus r, and you can see we're using that factorial notation. Now I would like to point out, just be careful, we do not really call that as an exclamation point. Now you are using obviously the exclamation point in your factorial notation, but basically that's how we define factorial. So you would say n factorial divided by n minus r factorial, right? Okay, so just to show you how this formula works, so let's say out of a total of 6 options, we are only choosing 4. So that's going to be 6 factorial divided by 6 minus 4 factorial. And I kind of like how they have broken this down, right? So 6 factorial, of course, would be 6 times 5 times 4 times 3 times 2 times 1, which is our numerator. 6 minus 4 would, of course, give you 2. So that's 2 factorial, which is 2 times 1. So that's this guy here. So between your numerator and denominator, you will see that 2 and that 1 cancels out, which means you are left behind with 6 times 5 times 4 times 3, which actually comes out to be 360. So sometimes, breaking this down and canceling out what's common leaves you behind with just a smaller value that you have to calculate, and that ends up becoming your answer. So 360 in this case. Okay, so they are saying although example 6 was solved by using the multiplication rule, or you can think of that as being the fundamental counting rule, you can also use permutation to solve that answer. Okay, so let's look at, sorry, example 6. Yeah, so they are saying 5 locations were taken and then arranged in order. So you're taking all the 5 locations and you are giving it the top first location, top second, top third, top fourth, and the top fifth, which I guess that would be the last location. So out of 5, we are choosing all 5. So that's going to be 5 factorial divided by 5 minus 5, which of course becomes 0. But remember our factorial rule, 0 factorial is 1. So that's 5 times 4 times 3 times 2 divided, times 1 divided by 1, which would of course give you 120 different possibilities. So there's 120 different ways that you could arrange the top 5 locations. Now, specifically in example 3, they asked us to choose 3 from those 5 locations, right? So that means your n is going to be 5, r is going to be 3. So from a 5 total, we are choosing 3. So that's 5 factorial over 5 minus 3 factorial, which will of course give you 5 factorial divided by 2 factorial. Again, your 2 and 1 will cancel out, and then you're just multiplying 5 times 4 times 3, which gives you a total of 60 outcomes, right? So there's 60 different ways that you can arrange that, and go back and look at this. You had that same 60 here as the answer when we used the fundamental counting rule. So just 2 different ways you could have done this, with the multiplication rule or the fundamental counting rule, or you could have used permutation to come up with this answer. Okay? Alright guys, so let's take a look at our next example here. We're talking about a radio talk show host can select 3 of 6 special guests for her program. And so out of a total of 6 guests, she has to choose 3. So that's 3 out of 6. And they're telling us the order of the appearance, the order of the appearance is important, which means which guest you select first, which one you select second, which one you select third is going to make a huge difference in this. So since they are telling us specifically that the order is important, that means you are using permutation. So that's going to be a choice of 6 total guests, and she is only going to select 3. So as you can see, again, that's 6 factorial divided by 6 minus 3 factorial. 6 minus 3 gives you 3. So that's 6 factorial divided by 3 factorial. So here's the thing. You can write this out as 6 times 5 times 4 times 3 times 2 times 1, right? And then you're dividing it by 3 factorial, which would be 3 times 2 times 1. So these guys are still going to be the same numbers, and you can cancel them out. Or you can just leave them as 3 factorial and 3 factorial. So they would still end up canceling each other out, leaving you with 6 times 5 times 4, which ends up giving you a total of 120 different outcomes. So there's 120 different ways that she could select these 3 guests that she wants to basically have on her program, right? And so this is how your permutation can also work out to be. Alrighty, so that brings us down to example 8. This one is a school music director can select 2 musical plays to present next year. So that's 2 musical plays to present next year. One will be presented in the fall, one will be presented in the spring, right? And she has to pick from 9 different plays. So again, we want to know how many different possibilities are there. So in this case, in the example itself, they're not saying order is important, but obviously since we know that one play she's going to put up in the fall semester and one she's going to be doing in the spring semester. So of course that means your order is going to be important, and that means we are using a permutation calculation again. So out of 9 total possible musical plays, she's going to be choosing 2. So that's 9 factorial divided by 9 minus 2 factorial, or basically 9 factorial divided by 7. So you again break it down as 9 times 8 times 7, and you can just stop at 7 factorial, and then we're dividing by 7 again, right? 7 factorial. So these two 7 factorials cancel each other out, and you're just doing 9 times 8, which means there's 72 different possibilities on how she can choose which play she wants to put up in the fall and which one she wants to do in the spring. Okay, so that's still a lot of options to choose from. Alrighty. So this will now bring us down to our permutation rule 2, and this one is basically saying that in the previous examples, all items involving permutations were different, but what happens when some of the items are identical? And you will see what we're talking about here. So permutation rule here says the number of permutations of n objects when you have R sub 1 objects that are identical, R2 objects that are identical, maybe going all the way up to RP objects that are identical. And basically, if you were to add all those different objects, you would still end up getting a total of R as your, if you were to add all those R sub 1, R sub 2, all the way to R sub P, it would still end up giving you a total of N possibilities. Right? Okay. And then, of course, your permutation rule 2 is we still have R n factorial on the top, but then on the denominator, instead of having n minus r factorial like you saw in the other rule, you will see this is r sub 1 factorial, r sub 2 factorial, r sub 3 factorial, all the way till you get to the end of r sub p factorial. So each object is actually going to have its own factorial that you are dividing your denominator by. Okay? Okay, guys. So let's see how we can use this rule. So remember, this is our permutation rule 2. And as I was mentioning, they should still all add up to a total of n. So it's kind of like these examples where you will actually see the use of this second rule. So they are saying how many permutations of the letters that make up the word statistics can be possible. So you have to actually first count how many of each type of letters are there. So you can see we have 1, 2, and 3 S's, right? Then there is 1, 2, 3 T's. There is 1 A. There are 1 and 2 I's. And what is it? Just 1 C that's left behind. So in this case, if you add all of these, that's 3 plus 3, which is 6. 6 plus 2 is 8. Plus 1 is 9. Plus 1 is 10, right? So we have a total of 10 letters that we are using in the word statistics. So that's your n, right? So this guy will equal your n. So that's our 10 factorial on the top. And then you have 3 S's. So that's 3 factorial. 3 T's. So that's 3 factorial again. 2 I's. So that's your 2 factorial. 1 A. So that's 1 factorial. And 1 C, which is your 1 factorial. So that's how this little formula here is getting used up. So the total number of letters, 10 factorial on the top. And then for your R sub 1, R sub 2, R sub 3, those are going to be the individual letters and how many of them were there. So you can see we're breaking this down into 10, 9, 8, 7, all the way to 1 on the numerator. And then 3 factorial gets broken down into 3, 2, 1. 3 factorial again gets broken down into 3, 2, 1. 2 factorial is 2 times 1, and then 1 factorial and 1 factorial. So you can do this however you want to, but I would definitely say 3 times 2 times 1 can cancel out with these guys. You can think of 3 times 2 being 6, so 3 times 2 with 6 can cancel out. And then if you wanted to reduce, this 2 can go into this 4 2 times. and then you can multiply the remaining numbers. Now you just have ones left on the bottom, so you know anything divided by 1 is the number itself. And if you go through all of those calculations, you end up getting a total of 50,400 different permutations. So if you just take the letters that make up the word statistics and you just arrange or rearrange those letters, they may not make up a word, but you can still arrange those letters. So there's 50,400 different ways in how you can arrange these 10 letters that are making up the word statistics. So this is kind of what your permutation rule 2 is looking at. So, you know, you can think about this in terms of code breaking again, right? Or passwords and stuff like that. That's why they tell us to make our passwords as complicated as possible, so people or computer programs have a hard time breaking your passwords down. So as you can see how these permutations or these counting rules come into play. All right, so this was our example for permutations using rule 1 and rule 2. Now let's get into combinations. So suppose that there's a dress designer who wishes to select 2 colors of material to design a new dress, and she has 4 colors on hand. So out of 4, she wants to choose 2 colors, right? Now the question we have to ask ourselves is the order going to be important in this case? Okay, so out of 4, we are choosing 2. So they are saying this type of problem will be different where we were talking about order being important. Here we are saying the order of selection is not important. So they're saying if the designer selects yellow and red, this will be the same thing if they selected red first and then yellow, right? So as long as the order is not important, that is where you use the combination rule. And that's really the main difference between your permutation and combination calculations. So basically the order or arrangement, the order or arrangement of your objects are not going to be important when you're talking about a combination, but order is important when you're talking about a permutation, okay? So selection of distinct objects without regard to order is what we call as a. All right, so let's take a look at this little set of example here that we have. So they're saying the difference between a combination and a permutation can be shown by using the letters A, B, C, and D. So if you did a permutation, right? So from a permutation, you would have, and we're choosing 2 letters at a time, right? So that's AB, AC, AD. Then you have BA, BC, BD, CA, CB, CD, and then DA, DB, DC, right? So all the different ways you can combine those 2 letters in there. And that's a total of 1, 2, 3, 1, 2, 3, 4. So 3 times 4, that's a total of 12 different outcomes. Or actually, I think I want to call it 12 different possibilities, right? Okay, so in this case, since the order is important, since the order is important, AB is not the same as BA, right? CA is not the same as AC because you're selecting A first and then B, or you're selecting B first and then A, right? So that's going to make a big difference when you're talking about permutations. Now, when we're talking about combinations where we're saying we have no regard for order, order is not important. So in combination, your AB is considered to be the same as BA. And like I said, in permutation, they would be considered to be different, right? Okay, so that means when we are looking at combinations, you can take all the duplicates out. So since AB and BA are the same, you can remove BA. Since AC and CA are the same, we can remove CA. AD and DA will be the same, so again get rid of DA. And then same thing here, BC would be the same as CB, so CB is gone. BD is the same as DB, so DB is gone. And then of course CD would be considered the same as DC, so that is gone. And you can see we are left behind with AB, AC, AD, BC, BD, CD, and those are all the options that you have here. And as you can see, this only comes out to be a total of 6 possibilities here, right? Okay, so they are saying once the duplicates are removed, what you are left with are these combinations here. And again, as you can see, they went down by half, right? You had 12 possibilities for the permutations, but now you only have 6 possibilities in the combinations, right? Okay. And they're basically saying the way we did the cancellations was we just kind of kept them in alphabetical order, so you can kind of read this little paragraphs that you have here just to get a little bit more understanding. Okay, so they are saying combinations are used when the order and arrangement is not important when you are doing your little selection process. So if you have a committee of 5 students, but you have to choose from a total of 25, so it really wouldn't matter who you selected first, who you selected second. So in this case, we are just saying as long as you choose 5 students out of those 25 students, you are good to go. So for your combination rule, we're also still looking at n as our total number of possibilities or options that you have available, and then you are selecting r from that. So instead of using the letter P, we are now using the letter C to represent our combination, but you should notice that the formula is very similar to your permutation formula, which was n factorial divided by n minus r factorial. So the only difference is we are now bringing in this r factorial as part of our combination rule. So just to change it from permutation to combination, you also end up dividing by r factorial, because that r factorial that you're dividing by is getting rid of any repetitions that you might have. So that's what that little r factorial does. All right, so let's look at our example 10 over here. So they are telling us how many combinations of 4 objects are there if you are taking 2 at a time, right? So there's a total of 4 objects. We're only choosing 2. So that's total of 4, choosing 2. So that's 4 factorial divided by 4 minus 2 factorial. And then again, you have that 2 factorial extra. So 4 divided by a quantity of 2 factorial times 2 factorial. So you will notice they are actually canceling out. You know what, I'm gonna write this out so you can kind of see what they are doing. So we have 4 times 3 times 2 times 1 on the numerator, and then you have 2 factorial times 2 factorial on the denominator, right? So 2 times 1 can cancel each other out, and then this is kind of what they're showing you here. This 2 cancels itself out with this 4. 4 goes into 2 times, and you are left with 2 times 3, which gives you the total of 6 outcomes. So this example 10, you can actually think about what we did here with A, B, C, and D. You had 4 possibilities because that's those 4 letters, A, B, C, and D, and we were pairing them 2 at a time, right? A, B, A, C, C, D, that kind of thing. So you can see with the combination, you ended up with 6 possibilities, and that's the same answer you have here in example 10. So that's the same result as your ABCD example. Okay. So as I was talking about, your formula for the combination rule is basically the same formula as your permutations, with this r factorial being added to the denominator. So you can kind of think of your combination rule as permutation rule divided by r factorial. Okay, and as I was telling you before, the r factorial get rid of any duplicates that you would have from your permutation calculation. Okay, and then you can kind of read this little paragraph here just to kind of get a little bit more understanding. I've talked about this, but you can kind of read through this, and then this little note here would be important when you are taking n combination with n, right? Because this would end up becoming n factorial divided by n minus n factorial, and then divided by n factorial. So you would end up getting n factorial, n minus n would be 0 factorial, and then n factorial. And remember, 0 factorial is 1. So you're basically just looking at n factorial divided by n, which would end up giving you 1. Okay? So that would be kind of on the side with this guy. Okay. All right, let's look at example 11 here, folks. So they are saying the director of movies in the park must select 4 movies from a total of 10 to show at this event, right? So how many different ways can we make the selections happening? So again, you kind of have to think, does it matter how they select those movies? Does it matter if they pick such and such movie as the first one or such and such movie as the second one? So since order is not important, you use combination. If order was important, we would have used permutation. So from a total of 10, we are choosing 4. So again, using our combination formula, you can see what this comes out to be. And then clean this up, and you basically end up getting 210 different ways that you can select 4 movies out of a total of 10 movies. And again, as I said, the order was not important here, and that's why we went with combination. All right, let's look at this one here, number 12. In a club, there are 7 women, 5 men. They want to choose, for a committee, they want to choose 3 women and 2 men. So what are the different possibilities that you can have here? So in this case, you have to think about, there are 2 groups, right? They want to choose women and they want to choose men. From 7, they want to choose 3 women. From 5, they want to choose 2 men, right? So that means you're actually going to have to do a calculation for each gender here. So to select 3 out of 7 women, we're going to be using combination 7 out of 3, which will give us 35 different possibilities. And then from the men, we are choosing 2 out of 5. So that's going to be a combination of 5 out of 2, which ends up giving you a total of 3 different ways. So 35 ways in which we can choose the women, 10 ways in which we can choose the men. So now you have to bring those 2 answers together, and this is where we would actually bring in our fundamental counting rule again. So that means you're going to multiply 35 times 10, which will end up giving you a total of 350. So you could actually write it out like this. 3 women out of 7, 2 men out of 5. So you would be taking each combination calculation, multiplying them together, and you end up getting a total of 350 as your outcome. So there would be 350 different ways that they could choose how they want to create this committee for this club. So I hope this kind of helps you out to see when we use the different types of counting rules and what we need to do for those, right? Okay, so this is just your summary of the different rules we have looked at. And now let's go ahead and look at some of our examples from the textbook, okay? Okay, so we are looking at our textbook examples here. The first one I actually want to start out with is this number 2 right over here. Let me see if I can make this guy bigger. There we go. List all the permutations of the letters in the word math, okay? So kind of like what we were doing with that example that had the word statistics, but in this case, they actually want us to list all the permutations, which means list in how many different ways you can arrange the letter in the word math, right? So that's of course 4 different letters in there. And I've actually taken a shortcut and I've already put the answers in, because otherwise this guy takes a pretty long time to show you all the different answers. So the idea here is you can do math, then you can do maybe just change the places of A and T, and you could have MTAH, which would be one of the permutations for the word math, right? So there's so many different ways that you can do these arrangements. So that's kind of what I wanted to show you here. Okay, so the first thing I actually want to show you, we have math. That's 4 different letters, and when we are doing our permutation, we are of course keeping all 4 of those letters, right? So that means our permutation would be 4 factorial, and then 4 minus 4 in this case, which would be 4 factorial divided by 0. 4 factorial would of course be 4 times 3 times 2 times 1. And then 0 factorial of course is just 1. So when you multiply, 4 times 3 gives you 12. 12 times 2 gives you 24. So you are looking at 24 different possibilities, right? So here's the deal. Like I was telling you before, you can have math, then you can have, just by switching the order of A and T, you can keep MA the same, but then you can change the order of H and T. So this is basically 2 different ways of writing that. You could also keep it as MT, but then change the location for your A and H. And of course, you know, you can keep going, because remember, there's a total of 24 different possibilities you are looking at. So this is kind of what I was talking about, where I took the shortcut. These would be the different combinations in how you can write the words, the letters that make up the word math. So you of course got math here, and then MTAH, which is one of the options here. MAHT would be this guy here. MTHA would be this guy here. And then look at how all those other different possibilities come out to be, right? And you can see that's 1, 2, 3, 4, 5, 6. 6 rows, 4 columns. So if you just multiply 6 times 4, you get 24. So you can see we have a total of 24 possibilities here. So in this case, remember, the wording of the problem was important, because they were saying list all the permutations. So that means they actually wanted us to write down all of these different permutations for that word math. So this is actually the answer for our example number 2 over here. Okay? Alrighty, so let's see the next example that I wanted us to work on is actually number 13, and we're not going to do all of them. I think I have parts A, F, and G selected for us. So let's take a look at those. A, which is 11 factorial. F, which is permutation between 12 and 8. And I think I said G, which would be the permutation between 7 and 7. So let's take a look at these guys over here. So this is 13. We'll do part A first, which is 11 factorial, right? So 11 factorial is just simple. 11 times 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, 1. Now, you know, the best thing is you guys actually have a factorial key in your calculator. Now, depending on what calculator you have, you will need to find those. My calculator, which is a TI 30X2S, has a button that says PRB for probability. So PRB, and under that you will actually find the factorial key. And unfortunately, if you don't find the key, you will need to write it out and multiply all those digits. So this will come out to be, once you do your calculation, it comes out to be 39,916,800 different possibilities. That's a lot of different possibilities to go through, right? Okay, so the next one we were going to look at was part F, and this guy is from a total of 12 options. We are choosing 8, so that's 12 factorial divided by 12 minus 8 factorial. And so of course 12 minus 8 will give you 4. So of course that guy will then become 4 factorial, and the way you can again write this out, 12, 11, 10, 9, 8. I might need to move this to the bottom because I don't think I have enough space here. So let's write it down here. That would be 12, 11, 10, 9, 8, 7, 6, 5, and then actually at 4, you can stop at 4 factorial, right? So 4 factorial and 4 factorial will cancel each other out, and then you're just multiplying the remaining digits. And again, you can use your calculator to actually again use the permutation I guess button or whatever you have on your calculator. Again, like I said, guys, you will kind of have to play around to see this, or we could try and do this through email, through pictures or something like that. But normally there's a PRB key, or you should see the little NPR or NCR keys, and for the factorial you'll of course see the little exclamation part. Anyway, so like I said, we can talk about that if you like. But if you do from a total of 12 options, selecting 8, and this is a permutation, which means order is important, you are going to have 19,958,400 different possibilities. Let me just put this around our answers. And then this was part F. And then one more that I wanted to talk about was part G. And this was just because you were choosing all 7 out of the 7 different possibilities. So that's going to be 7 factorial, 7 minus 7 factorial. So of course 7 minus 7 is 0. So you basically just get 7 factorial over 1, or you're just looking at 7 factorial as your answer, because anything divided by 1 is the number itself, right? Again, just to show you, if you're writing it out, that's just 7 factorial, and that will give you a total of 5,040 different possibilities. Okay? Alrighty. So just to kind of get you guys a little practice with the factorial and permutations. Now, let's look at another example here. I have number 20 selected for us. So let's see what this guy is talking about. This one is saying a particular cell phone company offers 4 models of phone, 6 different colors, and each of these are available with any one of the 5 calling plans, right? 4 models, 6 colors, and 5 calling plans. So they want to know how many combinations are possible. Now, one thing I will tell you, do not get thrown off by the word combination here, because just because they are saying how many combinations are there, they do not necessarily mean you are looking at combination rule as your calculation. So it's not necessary that you are doing the NCR calculation here, okay? So you just kind of have to see what the example is talking about. So this guy, number 20, is actually an example of using the fundamental counting rules. So what you would do here for number 20 is basically we have 4 different types of phones, and they told us there were 6 different colors, right? And there were 5 different calling planes. So using our fundamental counting rule, you would basically take 4 multiplied by 6 multiplied by 5. So multiply all those 3 numbers and you get a total of 120 different possibilities here. So you can choose you can choose one phone, one color, and one calling plan, and based on that you would have 120 different ways that you could select those. Okay, so pretty straightforward, right? But like I said, just be careful about, just because they said how many combinations are there doesn't mean they were actually asking you to use the combination rule. Okay, alright guys, so for our next example, I've actually got number 26 here. So this one is talking about an investigative agency has 7 cases and they have 5 agents, right? So in how many different ways can the cases be assigned if only one case is assigned to each agent? So this then begs us to think about, are we looking at order being important or not? So let's kind of think about this. So you've got 5 agents and you've got 7 cases to assign. So let's say we pick our first agent and we assign him a case, right? So if we've already assigned him a case, which means we got to take him out of the pool, him or her, right? Because they've already got a case, which means we won't be assigning them a case anymore. So then I'm only left with 4 different options or 4 different agents. And then from the remaining 6 cases, I would be assigning one of those 6 cases to my second agent, and so on and so forth, right? So what that means is that in this example, order is going to be important. And since order is important, we have to use permutation as our calculation, right? The permutation rule. So this is number 26, and I'm actually just going to write it here. So number 26, and we've got order is important. So out of 7 cases, we have 5 agents, so 5 of those will be assigned, and that means you are looking at 7 factorial, 7 minus 5 factorial, which would of course then become 7 minus 5 is 2, 2 factorial, so you're looking at 7, 6, 5, 4, 3, and 2, and you can stop at 2 factorial. Divide that by 2 factorial as your denominator, and then multiply those remaining answers. And if I have this done correctly, we should have a total of 2,520 different possibilities on how we can assign our 5 agents anywhere from those 7 cases. So you will have 2,520 different possibilities, right? Alrighty, so that would be example number 26. Now the next example I again wanted us to look at is going to be for our permutation rule 2, which is where we use the letters that make up the word Cincinnati and see how many different permutations are there. So you will notice this question is saying how many different permutations of the letters in the word Cincinnati are there. Like example 2 that we saw with the word math, they are not saying list the different permutations, right? These guys are asking how many different permutations. So you have to be careful about how they phrase these questions, and then based on that, you will see what your answer is going to be. So we are looking at the word Cincinnati. Okay, so let's go ahead and see what this calculation will be like. So this guy is number 32, and let me write that down. You've got Cincinnati as the word. Okay, so like I showed you in the example, we'll need to calculate how many of the each letter is there. So let's start with our list over here. So I'm actually going to do this on the side. We've got the letter C, the letter I, we have the letter N, C-I-N, we have the letter A, and we have the letter T, right? So let's write down for each of these. So as you can see, there are two letters for C, right? For I, we've got 1, 2, 3 I's. How many N's do we have? That's 1, 2, 3 N's. And then that leaves us with 1 A and 1 T, right? So that's going to be all of our letters. So 2 C's, 3 I's, 3 N's, 1 A, 1 T. Now if you add these numbers here, that will give you your N value, right? How many total letters do we have? Or you can just add up the number of letters in the word Cincinnati and go from there. But this will basically give us 5, 8, 9, and 10. So there's a total of 10 letters. And remember your permutation rule 2 was basically you take n factorial and then divide it by r1 factorial, r2 factorial, all the way till you get to r sub p factorial, right? So translating that into our example, we have a total of 10 letters, so that's 10 factorial. There are 2 C's, so that's 2 factorial, 3 I's, 3 N's, 1 A, and 1 T, right? So again, if we write all of this out, that's 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then I have 2 factorial multiplied by 3 factorial, another 3 factorial, and then 1 factorial and 1 factorial, right? So 3, 2, 1. Let's do this in color. 3, 2, 1, 3, 2, 1. They can cancel out, right? 3 times 2 is 6, so you can cancel it out with 6. And then I am left with a bunch of 1s, so 1s are okay. 2 will go into itself once, and 2 can go into 4 twice, right? So you would then be left behind with 10, 9, 8, 7 here. You are left behind with 5 and 2 from there. So you can do it that way, or of course, like I told you before, you can use your calculator formulas to help you out with. So if you go ahead and do this calculation, just make sure your calculations are correct, and this will come out to be a total of how many possibilities. So like I said, if your calculation is correct, this should come out to be 50,400 different possibilities. So the idea here is if we take those letters that make up the word Cincinnati, there are 50,400 different ways in how you can arrange those letters, okay? So that is how we use our permutation rule 2 to come up with this answer, and this was what, number 32? Yeah, okay? Now, the next example I actually wanted us to look at was just to kind of get you working with the combination rule. So we are actually looking at number 33, and I'm actually just going to do part B from here because all of these look so similar. So let's do part B, which is out of 8, we are looking at 3 different options, and this is for a combination. So number 33, part A. Alright, and that is 8 out of 3. So remember, your combination rule is 8 factorial, and then 8 minus 3 factorial, and then 3 factorial again. So that would be 8 factorial. 8 minus 3 is of course going to be 5. So that's going to be 5 factorial and then 3 factorial. Okay, so again, let's see how we can write this down. 8 times 7 times 6. And I'm actually going to stop at 5 factorial because I can cancel it out with the 1 on the denominator. And you know what? 5 factorial is fine, but I'm actually going to go ahead and spread out my 3 factorial. So 5 factorial and 5 factorial can cancel out. 3 times 2 is 6. So since 3 times 2 is 6, you can actually cancel out with this 6 on the top, which means you actually just end up multiplying 8 times 7. And 8 times 7, of course, you should know, will come out to be a total of 56 different possibilities. And as I was showing you in our handout earlier, this means that all those repetitions are taken out, right? And so you will have less number of possibilities with a combination than you do with a permutation. Alrighty. Now let's see. This was number 33. And I have for us to look at 36 as our next example. And let's see what this guy is talking about. So 36 is saying, how many ways can 4 baseball players and 3 basketball players be selected if you have a total of 12 baseball players and 9 baseball players, right? So you've got 12 baseball players, we only want to choose 4, and you've got 9 basketball players, and we only want to choose 3. So it just comes down to, do you think the order is important or not? If order is important, we do permutation. Order is not important, we do combination. So in this case, since they're not really mentioning anything about the order, we are actually going to make the assumption that order is not important. So how many ever baseball players you have, as long as you choose from those 12, 4 of them, it really doesn't matter who you picked first and who you picked last, okay? So in this case, that means we're actually going to be doing a combination calculation. And so in this case, since we're looking at 2 different groups of players, baseball and basketball players, the way this calculation is actually going to work out, and this is number 36, we have baseball players and we have basketball players. Okay, so they are telling us we are choosing 4 out of 12 baseball players. So out of 12, we are choosing 4. Yes, and then from basketball, it's 9. We are only choosing 3 of them. So you can see these are 2 different groups, which means we have to do a combination calculation for each group of players. And then this is where your fundamental counting rule comes into play, which means then we are going to multiply these 2 different options to get our total answer. Okay, so we're going to be multiplying these 2 sets. So let's see, for the 12 total, you're going to have 12 factorial, and then we're choosing 4 from those. So 12 minus 4, and then again 4 factorial here. For the basketball players, there's a total of 9, and then we'll do 9 minus 3 factorial. 9 minus 3, and then again 3 factorial here, right? So let's take each one of these individually. You have 12, and then of course 12 minus 4 would be 8 factorial. 4 factorial here, and then 9 factorial over here on the top, and this would be 9 minus 3, which is 6, and then again your 3 factorial. So just to go through this you have 12, 11, 10, 9, and I'll actually stop at 8 factorial. And then you've got 8 factorial, and I'm going to spread out my 4 factorial. So that's 4, 3, 2, and 1. And then we are going to be multiplying by 9 factorial. So that's 9, 8, 7, and again stop at 6 factorial. And then you've got 6 factorial, keep it as it is, and then write out the 3 factorial, which would be 3 times 2 times 1. Okay, so let's see what we can cancel out. 8 factorial and 8 factorial cancels out. 4 times 3 is 12, so 4 times 3 being 12, you can cancel out with the 12. 2 goes into itself once, 2 can go into 10 5 times, right? So here we would end up multiplying, there we go, everything else in the denominator cancel out. In the numerator you have 11 times 5 times 9 left behind, and then on the other side you have 6 factorial, that would cancel out, right? Now 3 times 2 is 6, but we of course have only 9, 8, and 7 left behind. So you can actually do this individually. 3 goes in itself once, 3 goes into 9 3 times, 2 goes in itself once, 2 goes into 8 4 times, right? So then you are left behind, everything else on the bottom canceled out. On the top we have left 3 times 4 times 7, and now you can multiply all 6 of these numbers because all of this is multiplication here. So when you multiply all of these numbers, and I think that's how we have broken this down, you should end up getting 41,580 different possibilities. So that's how we can choose all those different players. Okay? And again, if you, like I said, find those NCR keys on your calculator, then you may not have to break this down by hand and get your answers that way. But again, remember, since you're multiplying 2 different combinations here, parentheses are going to be your friend. So just make sure you're using parentheses for this calculation here. And I'm just checking, and I think those were the only examples that I had for us to do right now in this lecture. And then when we meet in class, I will go over more examples with you. So just look through these examples and let me know if you have any questions. And this was the, like I said, the last section we were going to be doing in chapter 4. So this is your 4.4 lecture. Okay, so let me know again, guys, if you have any questions, and I will see you in class next time. So be careful. Take care, guys, and see you then. Bye-bye.